Hi there, grade 11s, and welcome to today's lesson. What we're going to be doing is we're going to be doing some revision for paper 2. So remember that paper 2 is all your chemistry stuff, okay? And so we need to just remind ourselves what we've done in chemistry for term 1 and term 2. And you'll see that most of it has to do with moles, okay? And what I didn't put in here, but I'm going to put in, is gases. Okay, so most of the things have to do with moles. So there's one way of, what's a terrible color? There's one way of calculating moles. There's another way of calculating moles. This is concentration. Okay, it's all about the ratios. When you balance an equation, you need to know what the mole ratio is. Okay, so we've got a mole ratio. Then we talk about excess or limiting reagents, where we've got too much or not enough. Okay, and then with our gases, we had a few laws. So I'll write them in quickly. We had Boyle's law. Can you remember what Boyle's law was? It was P1 V1 equals P2 V2. And then we had Charles's law, and we'll put Charles's law over here. Charles's law was, in fact, it was volume, not pressure. It was volume over temperature equals V2 over T2. And then we had Gr11, his was pressure and temperature, P1 over T1 equals P2 over T2. So can you see what's happening is that a lot of what we've done in term 1 and term 2 has been with calculations. Okay, there's one part to do with theory that I'll talk about now, but let's just give the last one, PV equals nRT. Remember the ideal gas equation. Okay, and then if you remember back in term 1, we were dealing with shapes of molecules. So we spoke about if something is tetrahedral, or if it is trigonal planar, or if it is just linear, is it angular? Okay, so all of these different things can be incorporated into your paper 2. Okay, so when you are studying, when you're going through things, if you're going through past paper, and I've got some past paper questions for you today, just keep in the back of your mind that the thing about chemistry is that a whole lot of things can come together. I can ask you a question, or your teacher can ask you a question that's got moles, it's got something about the gas laws, and it's got something about the shapes of molecules. Okay, so chemistry is very much more interwoven, and things are linked a whole lot more than you'll find in your physics paper. Okay, but don't worry. I know you guys and girls have worked really hard this year, so this should be a breeze for you. So what we're going to do is we're going to start off and let's get going. So I'm going to start with this. Okay, remember I said to you about shapes, molecules, all those sort of things. So I've got the following question for you. I've got 5 substances. Consider the following molecules. A is NH3. You should know that's ammonia. B is CO2. Okay, that is carbon dioxide. C is C2H2. You won't have seen that before. It's called ethene, but it doesn't matter. Okay. D is H2O. That's water. And BH3 is E, and that's boron trihydride. Okay. Names don't matter, right? What is important here is that we need to be able to answer these questions. So hopefully you have a periodic table close by, and you'll need a calculator a little bit later, but right now we need a periodic table. Okay, so scratch quickly, find your periodic table while I start reading through the question. So the first question is, which molecule, number 1, contains a triple bond, 2 is trigonal planar, and 3 is angular in shape and contains a center atom with 2 lone pairs. Okay, so contains a triple bond. One of the substances contains a triple bond. One of the substances is trigonal or trigonal planar, and the third one is the other substance. One of the substances is angular in shape, and the molecule in the middle has got 2 lone pairs. Okay, so you're going to need your periodic table, and you're going to need to do a little bit of calculation about electronegativity. So I'm going to give you 2 minutes to answer these 3 questions, and then we'll come back and compare answers. So your 2 minutes is going to start now. everybody. That's your 2 minutes up. So let's compare answers. Right. Why do we need a periodic table? So I just want to show you quickly, because if you aren't sure of things, like you can't remember if it's got a triple bond or a double bond or anything like that, go and have a look at your periodic table. Remember how useful your periodic table is. Come on with the periodic table. Okay, it's definitely, there we go. Right. So your periodic table is really very useful. If you remember from grade 9, grade 10, you learned that your group number is associated with the number of bonds. So this will form 1 bond, that'll form 2 bonds, that'll form 3 bonds, 4 bonds, 3 bonds, 2 bonds, 1 bond. Okay, so if we go back and have a look at the question, and that's definitely not what I want. There we go. Let's have a look at our question. Our question asks us, which substance contains a triple bond? So if there's a triple bond, it must mean that one of the elements or 2 of the elements can form more than 2 bonds. All right? So that means we need to be, oh, come on. Today I'm definitely fighting with the computer. We would need to be looking, let's try again. There we go. We would need to be looking in either this group, or that group. So it either needs to be where there's 3 bonds or 4 bonds. Okay. So it's either going to have, let's say, boron, carbon, hydrogen, or boron, carbon, nitrogen, maybe aluminium. So let's see what we've got and compare. What do we have here? We've got nitrogen. Okay. But I find the easiest way to answer these is actually draw some pictures. So nitrogen will be 1, 2, 3, and it's got 2 at the top there. But look here, here's my hydrogen. So that's definitely not a triple bond. Okay, carbon dioxide. If I draw that, and I'll draw another one on this side. Okay, I don't think we're getting a triple bond here either. Okay, so that leaves us with C. I called it ethene. The actual name is ethine. So I need a carbon and a hydrogen, and a carbon and a hydrogen. And carbon can actually form 4 bonds. So here it's got 1 bond already with the hydrogen. So if I put, look here, we've got 3 bonds. But let's just check. Water, H. Here's my oxygen. No, there's no triple bonds there. And with my BH3, no, I might have 3 bonds, but they're 3 separate bonds, so it's definitely not that one. So the only one it could possibly be is substance C. Okay. Now, what about trigonal planar? What shape is trigonal planar? Trigonal planar is that shape. Okay, that means you'll have a molecule in the middle and then you'll have 3 others. So that means we need 4 atoms in total. Could it be ammonia? Let's have a look. This one's got 1, 2, 3. There's 4 atoms in total. But what shape is this going to give me? This is going to give me a pyramid shape. Okay, can it be carbon dioxide? Carbon dioxide is going to give me a linear shape, right? What about water? Water is going to give me an angular shape. That leaves us with BH3. So trigonal planar is going to be E. And we've answered the third one. It's angular in shape and it's got a central atom with 2 lone pairs. That is water, and that is going to be D. Okay, so do you see you're now using knowledge from grade 10, but also things that we've learned in grade 11 to answer a question like this. So let's see what else I've got for you. Goodness, I repeated the slide. Let's see. Next question. Which 2 molecules, okay, so 2 molecules can form a dative covalent bond with a hydrogen ion? Do you remember what a dative covalent bond is? Okay, if not, remind yourselves quickly and then we'll answer the question. Okay, I'm going to give you a minute to try and remember what a dative covalent bond is and answer the question. So your minute starts now. Okay, everyone, time up. That's your minute done. So, can you remember what a dative covalent bond is? So, a dative covalent bond, it says here specifically with a hydrogen ion, so it is going to be H+. What do we know about H+? It has got one proton. There's no electrons. Okay, so its orbitals are empty. And a dative covalent bond is still a bond where orbitals or electrons are shared, and this is the key point. One atom has got two electrons. Both electrons belong to the atom, so it's a lone pair. And the other atom has got nothing to share, but it just comes and takes over the space where the first two electrons are, and it pretends to share. Okay, so for example, my two molecules here are going to be A, and it's going to be D. So it's going to be ammonia and water. So ammonia looks like this. Okay. And the hydrogen ion is going to come and sit and share that one. It's not really sharing. It just takes over and tries to share the pair of electrons that the nitrogen's got. Another example would be water. So this will make NH4 ammonium. Okay. Water is another example. What the H+ does is it comes along and it shares. Okay, so remember, it doesn't bring anything to the bond. It just tries to share the bond or share the pair of electrons that belong to the oxygen. And we form something called H3O+, which is known as the hydronium ion. Okay. So now, this we can do. You should be able to. I've drawn a whole lot of Lewis structures. Okay, so we're going to do this one together. I want you to draw a Lewis structure of the CO2 molecule. In fact, I drew it for you earlier. Okay, carbon, 4 bonds. Oxygen, they form 2 bonds each. It is a linear molecule. So that means in the middle is going to be my carbon. I'm going to put 2 electrons there and 2 electrons there, because actually what happens is that the oxygen forms a double bond. Let's make some space here. So there's my 2 electrons that belong to the carbon. There's my 2 that belong to the oxygen. And there we go. And remember, I need to check that there's 8 electrons around. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 over there. And 1, 2, 3, 4, 5, 6, 7, 8. And I've got 8 over here. Okay. So I have got my 8 electrons on each side. And what does that give me? That gives me a nice linear shape, right? So now you have to briefly explain why the bonds shown in your answer to question 3 are considered to be polar covalent. And I want you to refer to the difference in electronegativity of the atoms involved. Okay, so that one's going to require some thinking. So what we're going to do is we're going to go off to an ad break, give you some chance to think about it. You're going to get a head start to think about this. When we come back from the ad break, we'll answer this question and then we'll compare our answers. I'll see you just now. Welcome back, everybody. I hope you managed to think about what the question was that I left you before the break, the electronegativity. I know some of you had to sort of scratch deep in your brains to try and remember that. Electronegativity, you need to know the definition. Remember, it's when 2 atoms are in a bond and it's the desire or it's the force of attraction or it's the attraction of one atom for the shared pair of electrons. So they must be in a bond, and it's the desire or the attraction of an atom for that shared pair. It's going to try and pull it closer to itself. So the stronger the electronegativity is, the more it's going to try and pull the pair of electrons in towards the nucleus. Okay, it's not going to pull it all the way in, but it's going to pull it closer. If it's a lone pair of electrons, then electronegativity does not apply. Okay, so how do we answer a question like this? The question was, briefly explain why the bonds shown in your answer to question 3 are considered to be polar covalent. So remember, polar covalent means that there is an electronegativity difference. There's a shared pair of electrons, but there is a bit of a pull either to one side or the other. So what you need to do is you need to grab your periodic table, have a look at the electronegativity differences, and then I think you need to give you a minute. to answer this. Okay, I don't have to write out a full explanation, just point form for me. I'll give you a minute to answer why you think these are called polar covalent bonds. And your minute's going to start now. Okay, everyone, time up. So let's have a look. So I need my periodic table. Okay. Now, on my periodic table, no, come back, periodic table. Okay. On my periodic table, what I'm looking for is my electronegativity. Okay, so remember, on this one, depends on which one you use, but this is the one that's normally given out. On the left-hand side of your block is your electronegativity. Okay, so I'm looking for carbon and I'm looking for oxygen. So my electronegativity of carbon is 2.5 and my electronegativity of oxygen is 3.5. So if I take the smallest number away from the biggest number, I'm going to get an answer of 1. Now the question is, in which direction is it pulling? It's going to pull towards the oxygen. Okay, why? Because the oxygen has got the greatest electronegativity. Okay, but now what does that mean in terms of answering our question? Okay, so our question was, explain why they are considered to be polar covalent. Okay, so we're going to say this, that oxygen has a greater, I'm just going to write En for electronegativity. So oxygen has a greater electronegativity than carbon. Therefore, that doesn't look right. I can't remember if there's supposed to be an E after it or not. So we'll put an E. Sorry if it's spelled wrong, guys. So oxygen has a greater electronegativity than carbon. Therefore, it will attract the shared pair of electrons more, and the bond will be polar. Okay, so as long as you got the fact that there's a difference in electronegativity, that it's attracting it more and it's causing polarity, you will get the marks for that answer. Okay, good. Let's have a look what else we've got. Okay. Still on intermolecular forces and those sort of things, we're now talking about boiling points. So the boiling points of 4 compounds of hydrogen, represented by P, Q, R, and S, are given in the table below. So we have to define boiling point and then explain the difference in boiling points between compound P, compound Q, compound P, and compound S. Okay, so I'm going to leave it like this so that you can see everything. I'm going to give you 2 minutes to answer this question, or both questions. Define boiling points and then explain the difference, and we'll come back and compare answers after that. So your 2 minutes is going to start now. Okay, everybody, time up. So let's compare answers. So first question was define the term boiling point. Okay, so what is our boiling point? Our boiling point is the point, I haven't given myself very much space here. Or let's just say, I'm going to say the temperature, because that's actually more accurate. The temperature at which a liquid becomes a gas. Okay, so it's the temperature at which a liquid becomes a gas, and it's all of the liquid. Okay, so it's not just a few molecules. All of the liquid's got enough energy now and it's starting to become a gas. Okay. It is also the point at which a gas will become a liquid. A gas liquefies. Okay, so remember it goes both ways. It goes either to a gas if you're heating up, or it goes from a gas down to a liquid if you're cooling it down. Okay, now we need to explain the difference in boiling points between compound P and compound Q. So compound P is CH4, and that's minus 164 degrees. Okay, so let me just draw out what I think CH4. So it's going to be a tetrahedral molecule. Remember I said to you I like drawing because it gives us a better idea of what we're looking at. And compound Q has got this. And here is the key. Compound Q has got a lone pair of electrons. So this makes this a polar molecule. This would be non-polar. So what does that mean? That means if it's a polar molecule, the intermolecular forces, so compound Q, I'm going to say here is a polar molecule. Okay, intermolecular forces are stronger in Q. Okay, everybody happy with that? Because it's polar, you're going to have things like dipole. All right, dipole are really strong forces, so they're going to hang on to each other. You need a lot of energy to get them to let go, so that you can then give the energy to the molecules. Okay, compound S is SiH4. So it should have a similar shape to CH4, Si, and you're going to have your 4 like that. Okay. So if we have a look, our carbon is minus 164, our SiH4 is 112. So they've got the same shape, so what do we need to do? We need to go back to our periodic table and let's just compare quickly. Oh, come on. Periodic table. Play nicely. Right, so silicone is over here. Carbon is above it. Okay, so what do we know? What's going on here? Is this a halogen? Okay, so with the halogens, we have a difference in there's a major difference or change in their, well, not necessarily all the halogens, but with the change in their boiling point, what we're looking for, especially something that has got hydrogen bonding. Okay, so our hydrogen bonding, or our elements with hydrogen bonding that we should really be concerned about are nitrogen and oxygen in particular. SiH4, it might be a little bit bigger than carbon. Okay, so that would be, because we can't find any reason for it to be, oh, come on. Can't find any reason for it to be hydrogen bonding. So I would say that the reason here is that SiH4 is larger, or let's just put what compound is it? Compound S is larger, therefore has a greater surface area. And a greater surface area means Greater surface area means that you're going to have stronger intermolecular forces, and stronger intermolecular forces mean that your boiling point is going to be higher. So remember, we're comparing minus 164 to minus 112. They're both negative numbers, but just 112, minus 112, is actually a bit warmer than minus 164. So that means it is going to have a higher boiling point because the surface area of the molecule is bigger. Why? Because silicone is bigger than carbon. Okay, so what else have I got for you? All right, I want to go on to our calculation questions. Okay, here we go. So we're going to head into another ad break soon, but I want to remind us of our gas laws. Okay, so what I've got here is 2 learners investigate the relationship between temperature and the pressure of an enclosed gas. That's important. Learners use different samples of the same gas in 2 identical containers of fixed volumes. Okay, so it's closed in and the volume is fixed. Okay, so we're looking for the relationship between pressure and temperature. Okay, what are we keeping constant? Our moles are constant and our volume is constant. Okay, so that's what they've told us at the top there. Graph P and graph Q represent the results obtained by the learners. Right. So let's just have a quick look at this graph. P has definitely got a steeper gradient than Q has. Okay. And the only thing that we've really been told is that it's a relationship between the temperature and the pressure of an enclosed gas. Okay, so different samples of the same gas. 2 identical containers of fixed volume. Okay, and that's what we get. Okay, so our number of moles is constant, our volume is constant. So first question that you'd be asked, remember I've said to you that we often lead you in to what the questions following are going to be, and the first question is your leading question. And so here you've got state Gay-Lussac's law in words. Okay, so what you're going to say is you're going to say Gay-Lussac's law states that when an enclosed gas with a fixed number of moles and a fixed volume, we can say it reacts. What's a better word? Which, in fact, I'll say, let's start with the relationship between pressure and temperature of a gas with a fixed number of moles and a fixed volume is directly proportional if the temperature is measured in Kelvin. So in other words, I'm going to have pressure directly proportional to temperature, okay, if the temperature is measured in Kelvin. So if the pressure increases, I should expect my temperature to increase. If my pressure decreases, I should expect my temperature to decrease, and vice versa. If I increase my temperature, I'm going to increase my pressure. If I decrease my temperature, I'm going to decrease my pressure. Okay, so you need to put that relationship into words, okay, and it's done beautifully in your textbook, so a good idea is just to learn the definition that's given to you in your textbook. Okay, we're off to an ad break. I'll see you shortly after that. Welcome back, everybody, and I hope you're ready for this last bit. We're going to do calculation, calculation, calculation. Okay, so you need your periodic table, you need your calculator, and I know that you've got your brains with you, and I know that they're working, so let's get right into it. It says here, number 2, use the law in question 1 to determine the value of the temperature X shown on the graph in degrees Celsius. Okay, so what we're going to do is we're going to work it out, then we're going to have to write on the graph what it actually is. So what is the law? Because I'm going to give you a minute to work it out. You are going to use this. P1 over T1 equals P2 over T2 to do the calculation. Okay, remember my temperature here is Kelvin. We have to convert it back to degrees Celsius. So your minute to calculate this starts now. Okay, everybody, that was quick, but hopefully you've got it right and got it ready for us. Okay, so I'm going to put it down here. So I've got P1 over T1 equals P2 over T2. So our information was given to us on the graph. So my P1 over here is 100. That's my P2 over there. 298 is my T1 and X is my T2. That's the unknown. So what I'm going to do is I'm going to substitute in. I'm going to go 100 over 298 is equal to 150 over T2. Okay, so now I need to rearrange so that T2 is the subject of my formula. So I'm going to get T2 is equal to 150 times 298 divided by 100. And then that answer I'm going to find by using my calculator. Let's just pop the calculator over here. So I'm going to use my fraction, 150 times 298. And then I'm going to divide that by 100. 100. And that's going to give me an answer of 447. T2 equals 447 Kelvin. Okay, the answer was requested in degrees Celsius. So to go from degrees Celsius to Kelvin, I need to subtract 278. So I'm going to go 447 minus 278. So I need my calculator again. So come with the calculator. Right, 447 minus 278 is going to give me 169 degrees Celsius. Okay, so my X is now 447 in Kelvin, right? Or 169 degrees Celsius, right? Then the next question would be to explain using relevant formulae why graph Q has a smaller gradient than graph P. Okay, so why does graph Q have a smaller gradient than graph P? Okay, I'm not going to worry about the formula on that too much, and I'm not actually worry about you doing the question. Let's go through it together. So if you look at your graph, have a look here. This one is lower. So Q is in pink, P is going to be in the blue. All right, so P has got a steeper gradient, right? Q has got a lower gradient or a shallower gradient, if you want to call it that. Okay, we now have to explain why P has got the steeper gradient. Okay, why do you think P has got the steeper gradient? So let's see what it tells us at the top here. So two learners investigate the relationship between the temperature and the pressure of an enclosed gas. The learners used different samples of the same gas in two identical containers of fixed volumes. Graph P and Q represent the results obtained by the learners. Okay, so what is going on here? Because they say it's the same gas. They say that it's the same fixed container, fixed volume of container, but we've got two different graphs. Okay, what do you think graph P would actually be? All right, hopefully you're saying now that you think graph P might actually be an example of a noble, not a noble gas, an example of a ideal gas. And graph Q will actually be an example of a real gas. Okay, so that's one possibility, that P could be an example of an ideal gas and Q would be an example of a real gas. Okay, what else do you think could be going on here? We've got a shallower gradient in Q. We see that at 298, it's not 100 kilopascals. It's definitely going to be less, right? At 447 Q, right, would be approximately 100. So what do we have going on here? If we know we've got the same volume and we know that we've got the same, the only thing that could possibly have changed, okay, we made the assumption that the number of moles was constant. The only other thing that could possibly have changed is where it says here they use difference. In fact, let's just change the color here. The only other possibility, if this is not a real and ideal gas, only other possibility is actually that our number of moles between the two gases is different. So P has got a different number of moles in its container to what Q has. It's the same gas, but the amount of substance is different. Okay, so if it's not an ideal gas, for me, that's the only other thing I can think of is that they have different amount of moles. Okay, next thinking question. I want to go on to, there's another gas question. I want to go on to this. I want to go on to moles. Methyl benzoate is a compound used in the manufacture of perfumes. It is found that a 5,325 gram sample of methyl benzoate contains 3,758 grams of carbon, 0,316 grams of hydrogen, and 1,251 grams of oxygen. You have to determine the empirical formula of methyl benzoate, and then if the molar mass of methyl benzoate is 136 grams per mole, what is its molecular formula? Okay, so that's going to require some working out because there's two questions there. I want you to determine the empirical formula, and then I want you to determine the molecular formula, or the actual formula of methyl benzoate. Okay, so that's going to require 3 minutes. So I'm going to give you 3 minutes, and they're going to start now. Okay, everybody, that's your time up. So let's see if we can answer these questions. Okay, I seem to have left my... Let's see if we can get rid of this. Come on. There we go. And that we will just need to... Come on, delete. There we go. Now we've got some space. Right. Determine the empirical formula of methyl benzoate. So, we have got the information that there is 5,325 grams of methyl benzoate, 375 grams of carbon, 0,316 grams of hydrogen, and 1,251 grams of oxygen. So we need to know what the percentage is. So what you're going to do for carbon, okay, so for carbon, we're going to go 3,758 divided by 5,325, and you're going to multiply that by 100. For hydrogen, we're going to do the same. Okay, the number's going to change. 5,325. Okay, and then for oxygen, it's going to be 1,251 over 5,325, and multiply that by 100. So let's check quickly on our calculator. So we've got 3.758 and divide that by 5.325, and we're going to multiply that by 100, and our answer is going to be 70,57. So here we're going to make this 70,57%. 57%. Okay. Here we're going to go with 0.316 and 5.325, and we multiply that all by 100, and our answer is 5.93. So here we're going to have 5.93, and for our oxygen, we're going to have, come on, there we go, 1.251 and 5.325, multiply that by 100, come on, 100, and we end up with 23,49. Okay, now you should know with empirical formula what you do with that. What do you do now? Now we need to convert that to moles. So carbon is going to be 70,57 divided by 12. For oxygen, it is going to be 23,49, and you're going to divide it by 16. Okay, not by 32 because it's only one atom. Okay, we're not worried about it as a diatomic element. And hydrogen, we're going to go 5,93, and we're going to divide it by 1. So if we line up our carbon to hydrogen to oxygen, let's just work out quickly what they are. So we said 70,52, 70.52 divided by 12 for carbon. How do I know that? I looked on my periodic table quickly. Gives me 5,88. This is 5,93, and my oxygen is going to give me 23.49, and I'm going to divide that by 16. So that's going to give me 1,47, 1.47. So what I do, I divide them all by 1.47. And let's have a look quickly. So I'm going to get 5.93 divided by 1.47, and that's going to give me 4.05. So then my second one, let's have a look here, it's going to be 5.88 divided by 1.47, and that's going to give me 4. So both of these, when we round them off, come on, there we go. I'm going to have 4 to 4 to 1. So I'm going to have C4H4O. Right. That gives you your empirical formula. And then just to help you with the second part of the question before we go, it's 136 grams per mole. Okay. Work out what 4 carbons, 4 hydrogens, and 1 oxygen equals. So it's 12 times 4, 16 times 4 is 48. plus, what's this, 12 times 4 is 44, plus 1 more, so we're getting at 97, something like there, 87, right? And then if you times that by 2, if you times it by 2 and you get 136 grams per mole, then you know your formula should be C8H8O2. All right, if you're not sure, please check with your teachers. Guys and girls, best of luck for your examinations. I know you're going to do well because you've been working really hard, and I look forward to seeing you next time.